All right, today we're going to talk about the acid ionization constant. This week will be pretty important stuff, math heavy. Uh, I mentioned in the classroom stream the test would be next week. That's looking less likely, but there's plenty of time to finish this unit and the last unit. Everything's going to be great. All right, so the ionization of a general weak acid, we call weak acids HX. Remember, because acids are proton donors, so they have a hydrogen kicking around, that's a proton. If it ionizes water, it donates its proton to water, turning it into hydronium, and then you're left with the conjugate base of our original weak acid. Okay, nothing new there. We can talk about equilibrium constants for this. Okay, remember it's products over reactants. There are never any coefficients other than 1 in an ionization of an acid or a base, so there's no powers to worry about. We crossed off water because it's a liquid, although I'll talk about that a little bit in a minute. So this is just the equilibrium constant for the ionization of an acid. We call it Ka. All right, so the final form looks like this. So it's the hydronium multiplied by the conjugate base concentration divided by the concentration of the weak acid at equilibrium. All right, we're going to be using this a lot. Now, a couple things. Your table of the relative strength of acids, okay, looks like this. It's organized by Ka, so a higher Ka means there's more hydronium, stronger acid. But Ka for the strong acids is called very large. There's a good reason for that. Strong acids ionize quantitatively, so if you go back to the ionization, there's pretty much none of this left over, and just it all turns into hydronium. So it'd be hydronium concentration divided by basically 0. Okay, so that's why it's called very large. It's a math reason. The acid concentration becomes pretty much 0. It all became hydronium. Now, Ka values are only accurate to about plus or minus 5% because the water concentration does change. You don't need to go deep into why water concentration changes. It has to do with just the way that it interacts with acids, how the ionization occurs. But you do need to know that these Ka values aren't super precise. Okay, they're only good to about 5%, like I said, and that will have consequences that you'll see a little later on. All right? There's two common types of problems that we're going to go over today. The first one I've already got set up here. It's calculating Ka when you're given a concentration or a pH. So I've given you the concentration of a weak acid and its pH. We're going to find Ka for this acid, and I've just written down some things that are going to help us. Okay, we don't know what this acid is, so I'm just calling it HX. This is the ionization. This is how we're going to calculate Ka. All right, but we don't know these values yet. Okay, we know what H3O is from the pH. We can get that, so let's go ahead and do that. So, at equilibrium, we just got to do this guy here. 10 to the power of the negative pH will give us that concentration. I get 9.77 times 10 to the negative 4. All right, so we know the H3O concentration. But we still don't know these guys. Remember, this is the equilibrium concentration. It might be a bit different than that. We're going to see that right away here. Okay, because in fact, to solve this problem, we're going to use an old method from this unit. We're going to make an ICE table, or an ICE table. Okay, so HX started at 1.15. Water doesn't matter because it's a liquid. Okay, these guys start at 0. And we just figured out the equilibrium concentration of hydronium right here. Okay, which means its change was this. Okay, so maybe you're shuddering because you wanted to leave ice tables in your past. Don't worry, acids and bases, the ratio is always 1 to 1 to 1 to 1. There's not much to do here. And the conjugate base concentration is always just equal to the hydronium concentration. These two are the same. Okay, we can subtract that amount from the weak acid concentration. It won't change things too much, but I'm going to do it. Like, mine becomes 1.149. That's worth writing. Okay, it's a bit different. So check us out. We can calculate Ka now. We have hydronium, the conjugate base, the weak acid. So let's throw these values in here. Okay, one thing I'm going to point out is I'm going to keep this exact value to get the best possible answer. So if you're not like super skilled with your calculator, check out what I'm going to do. I'm going to square this because it's the same thing multiplied, and then I'm going to divide by the answer that's on my screen to get that. You do second function negative sign. This is going to be the best possible answer. So I get 8.31 times 10 to the negative 7. That's my Ka. There are no units, and that totally looks good.